6.2. So first, please copy the vocab. You can pause the video. So just a little explanation of what you're seeing here. When it says no radicands, remember the radicand is the number under the radical. No radicands are divisible by perfect nth powers. So that means if you're doing a cube root, you can't have a perfect cube under the radical that could be factored out. No radicands are fractions, and then no radicals in the denominator. And for conjugates, so if you have a situation where it's a root b plus c root d, the conjugate is a root b minus c root d. So you just change the sign and vice versa. And like radicals have to have the same index and radicand. So like fourth root of 2 and fourth root of 2, those are like radicals. So if you take a look at this chart in your notes, you'll see it's the same laws of exponents that you have on the piece of paper that you got last class. It's just now that we're using fractions. So all of their examples over here illustrate the property with a fraction. So it's really nothing new. And it's that last row on that exponent sheet that I said that you would not need to understand yet. Well, now is the time. Now this is an explanation of that bottom row on your laws of exponents sheet. And then here we have the properties of radicals. So when you are multiplying radicals, you can put them together under the same radical, and when you're dividing radicals, you can put them together under the same radical. Notice that there is no addition or subtraction property. You can't do this with addition and subtraction. You can only combine radicals with multiplication and division. If this is the same index, so they have to have the same index. They don't have to be like radicals to be multiplied, but they have to have the same index. Again, they don't have to be like radicals. They can have different radicands, but as long as they have the same index, the same root, then you can put them as one big fraction with one big radical. So now looking at the notes, we're going to apply these exponent properties using fractions. So again, the rules are the same. So since I have the same base, I can add these fractions on number 1. And 3/4 plus 2/4 is 5/4, so 2 to the 5/4. Number 2, same base, so I can subtract these exponents. This is 3 to the 1 minus 1/4, which is 3 to the 3/4. Number 3, since these are both the same power, I can use that power of a quotient property and think of this as 20 over 5 to the 1/2 all to the third. And 20 over 5 is 4. So we're now looking at 4 to the 1/2 to the third. And square root of 4, 4 to the 1/2, square root of 4 is 2, and 2 to the third is 8. And number 4, these bases are not the same, so I cannot add the exponents, so I can just do a power to a power. So this is 5 to the 1/3 to the third times 7 to the 1/4 to the third. So multiplying power to a power, I just get 5 to the 1 here, so 5. And then 3 times 1/4 is 3/4. So then this is just 5 times 7 to the 3/4. Looking at number 5, we are looking at two radicals that have the same index, and so we can use the product property because the radicands don't have to be the same. The indices, which is the plural of index, just have to be the same to multiply. And I'm going to multiply them because 4th root of 27, that's not a perfect fourth. I don't know what that is, and neither is 3. So if I multiply them together, 27 times 3 is 81. So I've just multiplied, the step that I just did in between here was this. Multiplying them under the radical together. So that's the 4th root of 81, which is 3. On number 6, kind of the same approach, sorry, not times, this is equal to one big fraction because the roots are the same. I can go ahead and do this. And 250 divided by 2 is 125, and the cube root of 125 is 5. Number 7. We're going to simplify this the same process that we use to simplify square roots. You know, when we simplify a square root, we try to pull out a perfect square. When we simplify a cube root, we pull out a perfect cube. And so you think about the perfect cubes, that's like 8, 27, 64. So we want to find something that divides into 104. And if you do your little calculator trick, do 104 divided by x and your y equals, you will find that 8 times 13 is 104. So that means that we can write this as the cube root of 8 times the cube root of 13. And then the cube root of 8 is 2. So the simplified answer is 2 cube root of 13. On number 8, the first thing that I want to do is rewrite this as 5th root of 3 over 5th root of 4. Okay, now if this were a square root problem, then we would just multiply by square root of 4 over square root of 4 because it takes 2 square roots of the same thing to cancel them. But it's a 5th root problem. So we need 5 total 5th roots of 4 to make it all cancel out. So that means we need to multiply it by 4 more times. This is what I mean. Now they would all cancel and I would just get 4 on the bottom. And you might be thinking, is there a shorter way to write that? Yes. What we had here was 5th root of 3 over 5th root of 4. What we did was we multiplied it by, this was 4 to the 4th, so we multiplied it by 5th root of 4 to the 4th over 5th root of 4 to the 4th. This gave me, on the bottom, 5th root of 4 to the 5th, which is 4. On the top, I multiply 3 times 4 to the 4th, so 5th root of 3 times 4 to the 4th, which is 768. I'm not done yet, because now I've got to see if I can simplify 5th root of 768. And so since it's a 5th root, I'm looking to see, is there a perfect 5th that goes into 768? And again, if you do your calculator trick, 768 divided by x in your calculator, look at your table. I'll show you what I'm looking at over here. And I'm looking to see, is there a perfect 5th? You know, so like the first perfect 5th, 2 to the 5th, is 32. So let's see if 32, oh yes. So we've got 32 times 24 gives us 768. So that's going to be what we want to use. So we're going to write 5th root of 768 is the same thing as 5th root of 32 times 5th root of 24 over 4. And the whole point of picking that number was because that's a perfect 5th. 5th root of 32 is 2. So now we have this. And our last step is just to cancel the 2 over 4. That's 1 over 2. So this is just 5th root of 24 over 2. Number 9. So this is where the idea of a conjugate comes in. If I'm dividing by 6 minus root 2, the way to get rid of the radical in the denominator is going to be to multiply by its conjugate, 6 plus square root of 2. Now remember that the fraction bar is a grouping symbol, so these are understood parentheses. So I'm multiplying these together, meaning that I'm distributing. So in the top, I'm going to have 18 plus 3 root 2. In the bottom, so we're foiling here, 6 times 6 is 36. 6 times root 2 is plus 6 root 2. 6 times negative root 2 is minus 6 root 2. And then negative root 2 times positive root 2 is negative root 4, which is negative 2. So you see what happens here is the square root terms cancel. That's why this works. And so now I have 18 plus 3 root 2 over 36 minus 2 is 34. Number 10, this is just a matter of adding and subtracting, or subtracting in this case, like radicals. See, this is 7 times the 5th root of 12 minus 1 times the 5th root of 12. So 7, you can think of it as like 7x minus 1x, that's 6x. So this is 6 times the 5th root of 12. And it's just that simple. Remember, like radicals you can add and subtract, let me rephrase that. You can only add and subtract like radicals, and like radicals have to be the same radicand and the same index.